All right, hi everyone, welcome. I'm Stephanie and this is Judging, and today we'll be discussing our work on running large-scale shuffle on top of Ray Core. So this work is available in Ray 2.0 through the Ray Datasets library, and today we'll do a deep dive into why we did this and how it works under the hood. So first, a little bit about us. Judging and I are both software engineers at Anyscale, and we work on the Ray Core team. So we work on the infrastructure, basically supporting all of the libraries in the Ray ecosystem. The work that we'll present today is also in collaboration with researchers at UC Berkeley on how we can implement flexible and large-scale shuffle. So I also want to say a little bit about Anyscale. Anyscale is the company behind Ray, and Ray, of course, is a unified framework for scaling Python and AI applications. And the reason that we're building Anyscale is because we believe that scaling is a necessity for AI applications today, and it's also very hard to do. So the goal behind Anyscale is to provide a managed service around Ray applications, making it easy to build scalable applications for anyone. So without further ado, let's take a look at why we wanted to support large-scale shuffle on top of Ray. So to understand why we wanted to do this, let's first take a look at the broader Ray ecosystem. So Ray Core is a unified framework for scalable computing. It's an open source distributed framework that makes it easy to scale AI and Python applications by providing these core primitives around tasks, actors, and objects. And to make this even easier, in Ray 2.0, we've also built a unified toolkit that can handle different parts of building an end-to-end machine learning application. And we call this toolkit the Ray AI Runtime, or Ray Air. So the libraries in Ray Air handle different parts of a machine learning application, including things like distributed training, distributed model serving, and distributed reinforcement learning. And holding all of these libraries together is, of course, distributed data. So Ray Datasets is the key library for loading and passing distributed data between all of the other libraries in the Ray ecosystem. And a key primitive that's used in the Datasets library is Shuffle. And Shuffle is implemented directly on top of Ray Core. And this is what we will be talking about today. So to see how Shuffle actually fits in a real application, let's take this example where we want to do distributed data ingest for a distributed training application. So once we have significant data to process, this is actually going to be a pretty difficult task. So first we have to load the distributed data set from storage into memory, and we want to split this across a pool of distributed training workers. Eventually, we'll also want to train this on data that's larger than can fit in the memory capacity of the cluster. And to improve model accuracy, we'll also want to randomly shuffle the data set before loading it into the training workers. And finally, to improve GPU utilization, sorry about the text, not sure what happened there. To improve GPU utilization, we'll also want to pipeline this shuffling step with the training execution. So one thing to note here is that before Ray Air, doing this would actually require stitching together multiple different systems. So you might think about using one system for the shuffling step and then one system for the training step. But actually pipelining across these two is a pretty challenging task because now you have to stitch between these different systems. So with Ray Air, we can actually do this all within a single system by leveraging Ray Core. And a key part of that is, of course, doing this large-scale shuffle. So that's what we'll talk about next. OK, so what exactly is Shuffle? Shuffle is the key operation that's used in distributed map-reduce programs. So a map-reduce program is an application that can be split into two different stages. A map stage, where we apply the same function to each partition of a data set, and a reduce stage, where we aggregate the intermediate results produced by the map stage into a final result. So in between these two stages, we have a shuffle operation. And we call this a shuffle because we're taking one intermediate block from each map task and taking that into a reduce task to aggregate into a result, as you can see on the left. So one thing I just want to note here is that this is different from randomly shuffling the data set, which we showed in the earlier example. So the shuffle that we're talking about here is actually a generic system-level operation that's used in these higher-level applications, such as random shuffling, sorting, and group by. So why is shuffle difficult? Many of you have probably written a simple MapReduce program in Python before. So why are we thinking so much about large-scale shuffle? Well, the main problems that come at large scale are the fact that as the dataset size grows larger, the number of blocks that we have to transfer between map and reduce tasks is going to grow quadratically. So just as an example, if we think about a 100 terabyte data set, and let's say we split this into 1 gigabyte partitions, if we do this shuffle naively, we're going to end up with 10 billion intermediate blocks, and each of these is going to be 10 kilobytes. Now, that's actually not too bad if all of this can fit into memory. But even on a large cluster, you won't be able to fit a 100 terabyte data set into memory at once. And so what that means is that actually each of these 10 kilobyte blocks will have to be spilled from memory to a local disk. It'll have to be transferred across the network between the map and reduce workers. And finally, in the case of a failure, we'll actually have to recover the blocks. And so to handle this problem in the past, people have built a lot of specialized shuffle systems. So these are systems built specifically for large-scale shuffle. And the good thing about this is that because these systems are specialized, they're often very high performance. And that's because people have built them specifically for new application and hardware environments. But the cost of doing this is that there's actually a high development effort needed to build each new shuffle system. And in addition to that, because these systems are built only for shuffle, interoperability with other applications is pretty challenging. So if we think about the data ingest problem from earlier, if we wanted to build this with kind of the current shuffle systems, you would actually have to stitch together a shuffle system with another system built for training. So as part of this project, we wanted to see if there was a better way we could do this by leveraging Ray Core directly to build a flexible shuffle that could still handle large scales of data. And to see how this works, we can actually look first and take a contrast to how shuffle systems are being built today. And I'll call these monolithic shuffle systems because they're built directly on top of low-level primitives such as RPC. And then on top of the shuffle operation, we have these higher-level applications such as sorting and group by. So in collaboration with Berkeley, we actually built out this Exoshuffle project, which was seeing if we could use Ray Core's primitives directly to build shuffle in a way that was more flexible. So instead of building these shuffle algorithms directly over primitives like RPC, we can use the Ray Core primitives like tasks and objects to build the shuffle algorithm in only a few hundred lines of Python. And the other advantage of doing this is that we can now easily interoperate with other Ray applications, such as Ray Train. And that's because all of these algorithms are actually just using object refs under the hood. And so that's actually exactly what we did in Ray 2.0. So in Ray 2.0, users of Ray datasets can actually scale operations like random shuffle to over 100 terabytes and to more than 100 nodes. And so we still have a lot of work to do here, but we have some promising initial results showing that we can possibly achieve the same scale and performance as other monolithic shuffle systems. OK, so let's take a look at what makes all of this possible. So how is shuffle actually implemented in Ray datasets? Well, we have the Datasets library, which is going to implement the shuffle algorithm in Python. And this tells Ray Core what computations need to run and how to move the data between the different computations. So Ray Core will actually handle all of the hard parts of the shuffle execution here, including spilling data from memory to disk and loading them as they're needed, transferring the blocks across nodes, and recovering blocks in the case of a failure. And we can also take a look at how this works out on a real cluster. So here we have 2 Ray nodes. And in this diagram, we'll have the datasets library code, which is going to sit at the application driver. And you can think of this as kind of the entry point of your application. So from here, Ray Core will handle the actual shuffle execution, starting with placement and scheduling for the map and reduce tasks. Each map task here will produce some intermediate objects, and these will get stored in Ray's shared memory object store. And Ray will also handle spilling these to disk as necessary. Ray also handles the transfer of objects between nodes through its distributed object store. So here, as the reduce task is scheduled on the other node, we're going to transfer all of the map outputs over to it, where they can be aggregated by the final reduce task. So that was a high-level overview of the different components involved in Shuffle on Ray. And next, we'll talk about how the Shuffle is actually implemented in Python. So the simplest way to implement a Shuffle basically looks like the MapReduce program that I showed earlier. So here, what we're doing is actually taking the Ray core primitives of tasks and objects to create this DAG, which tells Ray kind of what the dependencies are between tasks. So here we have one map task for each input partition of the data set, and each map task will produce one output for each reduce task. And then, of course, we submit a reduce stage that aggregates these results. So there are actually a lot of different ways to implement a shuffle algorithm, and this is a pretty active area of research and development. So you don't necessarily need to follow all of the details of the algorithms that I'll show next, but you can take a look at the paper linked in the QR code, which is the Exoshuffle white paper. So a lot of the algorithms that people have designed are optimized to improve I/O efficiency. So usually what this looks like is taking these small blocks and merging them into larger blocks that can be written out as larger files or larger blocks over the network. Here's another variation called push-based shuffle, where we push the map outputs directly over the network and then merge them on the reduce side. So I want to stress here that actually all of these algorithms were designed and implemented as part of other monolithic shuffle systems. But the cool thing that we found is that by using Ray core directly, we could actually implement a lot of the same basic algorithms, but without having to rebuild an entire shuffle system. And the difference between these shuffle algorithms is actually pretty huge. So this is looking just at simple versus push-based random shuffle implemented on top of Ray. And on the left-hand side, we have the driver memory required to run the application. And you can see that the simple shuffle actually runs out of memory after about 2 terabytes of data. And that's because simple shuffle produces many more intermediate blocks, and this is adding a lot of metadata overhead to the system. On the right-hand side, we have the overall runtime. And you can see that these perform about the same after about 500 gigabytes, and that push-based shuffle continues to scale past that. So in datasets, it's actually pretty simple to choose between these different algorithms. All you have to do is just pass a flag into your program. And in the future, we'll also look at how we can automatically choose the best algorithm for your application. So it's actually pretty easy. Now we can also look at how we can actually implement these in Python. So I'll just walk through a simple example of a simple shuffle. So the parameters here are m for the number of map tasks and r for the number of reduce tasks. So first, we'll submit one map task for each input partition of the data set. And each map task here is actually going to return a list of object refs. And so these object refs are kind of futures that will point to the eventual value of the map task. And so all map out here is actually going to be a nested list of object refs, which we can now use to pass to the reduce tasks. So we'll take one output from each of the map tasks and pass this to a reduce task. And this tells Ray that we can't run this reduce task until all of those map outputs are ready and local to the reduce worker. So in between these steps, Ray will also spill and restore the objects as needed and also transfer them across the network as needed. So finally, we'll repeat this process for each of the reduce tasks. And this will now return a list of our object refs, which we can then pass on to another Ray application. And that's actually exactly what we do to implement ray air, or data ingest in ray air. So here, let's take a look at the actual code for the example that I showed earlier, where we want to do distributed data ingest for a training job. So here, we're first going to load the data set into memory from a list of Parquet files on disk. And then we're going to tell datasets the granularity that we want to execute the random shuffle at. So that could be the entire dataset size, or it could be just one partition of the dataset. Next, we'll actually invoke the random shuffle. And here, the repeat call will give us back an iterator that loops over the dataset. And that will allow us to actually pipeline this with a training step by parallelizing the shuffle operation with the training execution. And then finally, we can take this output and shard it across the pool of workers. So I think the cool thing here is that actually what's making all of this possible is the fact that all of these library calls are using ray tasks and object refs under the hood. OK, so next I'll hand it over to Jiajun to talk about some of the key ray core features that made this work possible.
Thanks, Stephanie. Next, I will talk about several key ray core features that power Shuffle on Ray. First, I'm going to talk about scheduling. So in order for the shuffle to be performant, the read, map, merge, and reduce task needs to be scheduled in a certain way. Specifically, there are two requirements. First, we want to balance the load to improve the cluster utilization and avoid data skew. Second, we want to reduce data movement across nodes. Now let's see how different ray scheduling strategies can be used to meet these requirements. So the first scheduling strategy is spread scheduling. Say here we have 4 read tasks that need to be scheduled. In order to achieve load balancing, we want to spread these read tasks across the entire cluster, so each node loads equal amount of shuffle data. This is how you can do it in code by specifying the spread scheduling strategy when submitting your read tasks. Now let's see how these 4 tasks are scheduled in a cluster of 3 nodes with spread scheduling. So the first read task will go to the first node, and the second read task scheduled on the second node, and the third task on the third node. The fourth read task go back to the first node. As you can see, the read tasks, they are spread among all 3 nodes in a round-robin fashion. The second scheduling strategy is locality-aware scheduling. As an example, here we want to schedule a map task that processes data loaded by its upstream read task. We want to schedule the map task to where the inputs are to avoid data movement. This is how you can do it in code. So unlike the spread scheduling, you don't need to explicitly specify a locality-aware scheduling strategy when submitting tasks. Ray will automatically do that based on the location information of its input objects. So by default, Ray schedules tasks to where most inputs are. Now let's see what if we don't have locality-aware scheduling. So the read task runs on the first node, and it saves its output to the local in-memory block store. And the map task runs on a different node. As we can see, if the map task is scheduled onto a different node, then the data needs to be moved across the network, which is slow. On the other hand, if the map task is scheduled on the same node as the read task due to data locality, then no data movement is needed. So the last scheduling strategy I want to talk here is node affinity scheduling. So here we want to schedule 2 merge tasks and 1 reduce task. So the goal, we want to collocate the merge task and the reduce task so that the reduce task can get its output of its upstream merge tasks without data movement. So let's say if we don't have node affinity scheduling, then the 2 merge tasks may run on 2 different nodes. Then no matter where the reduce task runs, some data movement must happen. So the solution is using node affinity scheduling strategy, which limits which node a task can run on. So this is the code how you can do it. First, you define a node affinity scheduling strategy with the target node, and then you use that strategy when submitting your task. So one thing to notice here is like we specify soft equals to true when defining the strategy, which means like we can tolerate the target node failure by running the task somewhere else. So let's go back to the example. With the node affinity scheduling, the merge and the reduce tasks, they are guaranteed to run on the same node. So as you can see, once they are collocated, no data movement is needed to run the reduce task. So the next great feature I want to talk about is object scaling, which enables out-of-core processing. So this is an animation showing like object scaling happens when a running task wants to create some object, but the local object store is full. So several things about object scaling. So object scaling is a process of scaling real objects to the external storage to make room for new objects. It essentially makes shuffling larger than memory dataset possible. So for the spared objects, they are restored when needed. Last, as an optimization, small objects, they are fused into a single file for performance. So the last Ray feature I want to talk here is fault tolerance. Ray has two mechanisms to provide fault tolerance to node failures. The first is task retry, which will rerun the failed task on other nodes. The second is lineage reconstruction, which is a mechanism to automatically reconstruct objects lost from distributed memory by re-executing the object's lineage, basically the task graph that created the object originally. Now let's see them in action. Here we have a DAG with 2 map tasks and 1 merge task. And now the merge task is running, and it merges the output of map task 1 and map task 2. Now let's say the first node fails. Due to task retry, Ray will try to rerun the merge task on a different node. Now let's say it's the third node. In order to run the merge task, we need the output of map task 1 and map task 2. But the output of map task 1 is also lost due to the node failure. So Ray will try to reconstruct the object by rerunning map task 1. And for the output of map task 2, it's still available in the cluster. So all we need to do is just copy it over. And after that, the merge task is ready to run again. So here is a real example. So this bar chart shows the runtime of a 1 terabyte shuffle chaos test with different number of injected failures. As you can see, the runtime is not linear to the number of failed nodes, which means like we don't need to restart the shuffle from beginning when failure happens. So to summarize, with RAID 2.0, it supports shuffling at least 100 terabytes of data. And it is now available through RAID Dataset and RAID Air. So in the future, we will focus on greater scalability, automatic out-of-memory handling, and auto-scaling, among other features. So here are the links to the RAID Dataset doc and the original Exoshuffle paper. So check them out if you are interested. And finally, thanks for attending the talk. Open for questions. If you have any questions, I think we still have some time.
Yeah, if you raise your hand, I think Thomas will be over with the mic.
Do you want to come?
Hi, thanks for the talk. I was just curious, you were speaking about node affinity, and you talk about scheduling, for instance, 2 map tasks together that will be, whose output will be consumed by the same reduced task. But I suppose when you create the map tasks, you don't yet know who's going to be their consumer. How do you make that work?
So for the map task, we don't use node affinity. It's like only between the merge task and the reduce task in the push-based shuffle case. Because like for the push-based shuffle case, the merge task output is only consumed by 1 reducer. So it's not like by multiple reducers. So that's why we can have the collocation.
Hi, thanks for the presentation. What happens when you exceed the 100 terabytes limit that you have up there?
Yeah, so right now, we still have some scalability limitations that we're actively trying to resolve. I think the main one right now has to do with the metadata cost still. So you can talk to us offline about that. But basically, because we're having to deal with all of these small blocks in the system, that's actually quite a bit of overhead for the system. And so yeah, we're thinking about ways to optimize that. Yeah, at the moment, it's not an area where we've focused a lot of work yet. Okay, cool.
Yeah,
Yeah, well, I
yeah.
think
Oh,
if that's
there's a-
it. Oh,
Thomas?
yeah.
Oh, sorry, 1 sec. Someone is.
Have you compared the shuffle performance between this and the Spark Shuffle?
Yeah, so if you check out the Exoshuffle white paper, you can see some performance numbers between the two. I think with these kinds of benchmarks, it's always a little bit hard to get like a good comparison because there's like a lot of different tuning that you can do. But so far, the results look, I would say, pretty comparable. Okay, well,
Yeah.
yeah, thank you if that's
Thanks
all.
for attending.
Yeah.